Okay, today's lecture is going to involve Riemann sums and the definition of the integral. Now, just a fair warning, um, this is going to be a bit of a longer lecture. So feel free to, take your time with it, go section by section. And I'm going to provide a little bit of an outline or a roadmap here, just to keep it a little organized and keep the story together. So, because basically what it is I'm going to do is I'm going to tell you a story, and this is how everything is motivated. And I think it's a little bit easier to understand this way, just because this is sort of a difficult topic. And I think phrasing it in this way is the best and most intuitive way. Okay, so first, we're going to talk about the beginnings of area. Then we'll move on to sum notation. This is a bit of an aside here from the story, but this is something that we sort of need, and it's a natural point to do it. Then we're going to learn about some sum formulas along the way. So this is a bit of an aside from the story. And then we're going to talk about estimating using Riemann sums. Then we're going to define the integral. And finally, we're going to do a couple of examples. I think there's only two. There might be three, but they're sort of long examples. So it'll certainly take up a good amount of time. And I'll try to put timestamps for each of these sections in the description of the video, so you can sort of skip around and get what you need to get out of these things. Okay, so let's talk about the beginnings of area. Okay. So for thousands of years, people wanted to know areas of various shapes, right? Sort of a natural question, especially if you're, trying to build a farm and you're trying to maximize the amount of crops that you can put on it, or minimize a fence around a certain thing, things like this. So these are natural questions, and the easy ones were found first. Easy ones being rectangle, right? This is just area equals length times width. Triangles, area in this case is 1/2 base times height. And circles, which of course we know is pi r squared, right? These are all things that the ancient people knew about, because they were sort of easy to figure out on your own. You can just sort of come up with them, along with some others, but these are sort of the most basic ones. But these didn't account for quote unquote weird or irregular shapes, like something like this. Or something like this, like a vase sort of a shape. Or even something like this, where this is sort of just a little section of like a river or something. If I'm looking to find out, how much water is in this, I would need to know the area of one of these cross sections, right? So say I have a river and I want to find out, well, what's the area here? There's no easy way to do it, right? This isn't a rectangle, and there's not even really pieces of this that I can carve out that look like regular shapes, right? It's all curvy lined, and it just doesn't seem like it fits into any of these categories. Okay, so what did they do? How did they get around this? If they needed to find out information, how did they figure out what these areas were, right? In a lot of cases, this was important. This was a matter of survival. And the best thing I could come up with was they just estimate, right? They did their best to get the shapes that they knew about to sort of fit into what they have, right? You could probably get like a little circle that lives in here, maybe a little rectangle over here, rectangle here, circle here, right? Just to sort of get an estimate, get it close enough, right? So now recall, remember from the beginning of the semester, I don't know if the other Nick explained it in quite this way, but when scientists were trying to find instantaneous velocity, they used estimates of average velocity, right? And I remember at one point toward the beginning of the semester, I wrote up, okay, here's one estimate, here's a better estimate, here's an even better estimate. And then the breakthrough came when the concept of a limit was introduced. Right? Now, I'm emphasizing this because I think a lot of people that take a calculus course miss out that calculus is simply the study of limits, right? The limit is the important thing. This is the thing that makes calculus work, right? It was, as soon as a limit was created, calculus was created. So when limits were introduced, the breakthrough came when the concept of a limit was introduced. And they were able to find a best estimate, right? The limit, really, when you think about it, is just an estimate, but it's such a good estimate that we take it to be the actual value. It's so close to the real value that we can figure out what the real value is simply by looking at this quote unquote perfect estimate. Now, why do I say this? Why am I bringing up, things like this, like derivatives, right? Because this is just a derivative. Once we take a limit of average velocity, we get instantaneous velocity, which is exactly the derivative of the position function. So why do I say this? Well, the same process took place when people wanted to find exact area. So this is the idea. This is the roadmap. This is what we're going to do. We're going to estimate, and we're going to calculate this sort of, it's not really an average area. That doesn't make much sense. It's estimating using shapes that we know, right? Taking these areas here, in particular, this one, and using them to estimate. Then if we take a limit, we're going to get the right answer. We get exactly the area that we're looking for. That's sort of looking ahead what we plan to do. Okay, so how are we going to do this? Let's look at a motivating example. All right, let's take that first shape that I looked at. This thing, whatever it is. Right? And we can look at this thing as a function which lives on the axes, right? X and Y axes. And this thing can be f of x defined on the interval, let's say 0 to 10. Let's just say it's 10 units long. Okay. All right. So now let's try to estimate using a rectangle. Let's just get a ballpark. So let's try to estimate this area using rectangles. And let's pick the naive thing and let's just take one rectangle and let's guess, right? So let's take the rectangle. I can put a rectangle sort of anywhere I want, but how do I get a close estimate? Well, let's define it by having the height of the function at this place here, right? So I'll define this to be the height because I just want to start it at 0, right? I want to get the whole thing. I don't want to miss any pieces. And let's just naively take one rectangle. So how I do this is I pick the point x equals 0. I find the f of 0 here, the height of the thing, put a dot, and then construct a rectangle using that. So I just draw this line straight over until I hit 10 because I only want one rectangle to cover this whole thing. And then I drop it down and I look at the area of this thing. Now, of course, this is an estimate, but it's not a great estimate, right? I'm missing this in here, or I'm counting this as extra, right? This is an area which lives in the rectangle, but not in the shape that I'm looking at. Same thing here, and same thing here. Now up here, that's all stuff that I'm missing with the rectangle. So, okay, maybe if we're lucky, this and all the things that I colored in dark and all the things that I sort of colored in with circles will cancel each other out. Maybe, maybe not. But again, this is just an estimate and we're getting a ballpark, right? So the point is the area of the rectangle is easy to compute. And it provides an estimate of the area, right? This is why we're using rectangles, because it's just length times width. That's something we can easily find out. The length, the height of it, is just f of 0, and the width is 10. Okay, we can multiply those two together and we can get an estimate of the area. Great. So okay, so the squiggle, this thing up here, right, just the top part of this shape, is written now as f of x. So we can now phrase the question of what's this area? as what is the area under f of x and between 0 and 10. Or alternatively, on the interval 0 to 10. Okay. All right, so what have we done? The new question we have is, what is the area under f of x on the interval 0 to 10? How we've attempted to solve it is we've taken a rectangle, which is defined by sort of the endpoints of the shape, and we're saying, all right, this is an estimate. It doesn't look like a very good estimate. It looks like we're missing quite a lot, but it's an estimate nonetheless. Okay, so we have area under f of x is approximately the area of the rectangle. And the area of the rectangle, like I said, is easy to compute. It's just f of 0 length times 10 width, right? Okay. But like I said, the estimate is pretty clearly crap. So how about more rectangles? Right? What if we start making more rectangles and thus making them smaller? Say 2 rectangles. Then I would take this guy, cut him off around a half, and then pick another one, which is defined again by the height of the function. So it would be defined up here. And then I have another rectangle up here. Okay, seems like that's getting a little bit closer. So what do I mean by that? Let's take a look and let's try some more rectangles. Let's try, because the width is 10, let's try not 1, but 10 rectangles. So again, here's f of x. This is the function which defines the top, and we're cutting it off at 10. And here's 0. All right, so let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I'll label every other just because I don't have a ton of room here. Okay. All right, so a little note, last time we used the left endpoint, right? We took f of 0, drew a line up, drew a dot, and then went straight over till 10, and then cut it right down. But we can use left or right. Endpoints to define the rectangles. This means that either I can start with my first rectangle being of height this here, and then drawing a rectangle over like this, or I can make my first rectangle start at the right side of that point here, and then drawing my line over to the left and straight down. And then, of course, down like this too, right? So these are certainly going to give me 2 estimates. It looks like if I define it from the right endpoint, I'm going to underestimate. And if I define it from the left, I'm going to overestimate. But these are just 2 different things. But in the end, it actually doesn't matter. So for the moment, let's just use left just for the one that we're working on. All right, so I want to construct 10 rectangles. So I do this. Then I come up to f of 1, I draw a dot, straight over and down. Come up to f of 2, straight over to 3, and then down. Make sure I finish it. F of 3, it actually looks like it meets that rectangle. It's not necessarily the case, but happened to work out here. There's my rectangle there. Go up to f of 4, straight over and down. F of 5, right here, straight over and down. F of 6, straight over, down. 7, f of 8, f of 9, and we're done, right? So now notice that, okay, I have this extra stuff in here, this extra stuff in here, this extra in here, and this extra right here. And then I miss, sorry, I didn't finish that one, this stuff from the shape itself, right? So I've colored in dark the places where I have an overestimate from the rectangles, and then I've sort of circled in the stuff that I have an underestimate of. Now notice there's definitely a lot less of that stuff colored in than there was up here, right? I overestimated quite a bit, and then I underestimated quite a bit. Up here, I'm only off by a little bit. So it does seem like more rectangles means better estimate. Okay, that's just something to keep in mind. That's something to build intuition a little bit. Okay, so notice now, similarly to last time, area of rectangles is still easy to compute. And it gives a better estimate of the area. Okay, so if we let the squiggle equal f of x, then the area under, not of, under f of x is approximately the area of the rectangles. And that is exactly equal to, I should write this a little bit more clearly. Now, if we let the squiggle equal f of x, then the area under f of x is approximately the area of the rectangles. And that is equal to the sum of areas of each rectangle, right? If I'm looking for the area of a bunch of rectangles, I can just take the area of the first one, plus area of the second one, plus area of the third, dot, 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 all the way up to the area of the 10th, right? So this algebraically is equal to length times width. The length is f of 0. This is how I defined the height of the rectangle. I went up to f of whatever the left endpoint was. In the first case, it was 0. And then I went over length 1. I have 10 evenly spaced rectangles, so each interval is going to be 1. Plus, now f of 1 times 1. This is, again, length times width, plus f of 2 times 1. again, length times width, plus dot, dot, dot. Keep going up until the last one, f of 9 times 1. And again, this is length times width. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 rectangles. Okay. So this is the end of 1. I'm going to take a brief aside now. And start in on number 2, which is sum notation. Okay. Now, returning to this, I have f of 0 times 1, f of 1 times 1, f of 2 times 1, dot, 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 f of 9 times 1, and they're all added up. Okay. This is a long way to write this, and with the dots here, it could be a little unclear, right? This is, I mean, we know what I'm talking about here, but perhaps in certain cases, these dots are, probably not great. Plus, it's a lot of writing. So there is a nice, compact, grown-up way to write a sum like f of 1 or f of 0 times 1 plus f of 1 times 1 plus dot, 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 plus f of 9 times 1. So the notation that we're going to be using is, this is a capital sigma. The reason we use sigma is because it means sum. S. Sigma is the Greek S, which I assume you all know. And capital delta we're going to use as well. Means change. We've used this before. I don't know why they use delta. That's a capital D in Greek. I don't know why. But it means change. Okay, so let's return to this example. I can't write. All right, so we have area of rectangles equals f of 0 times 1 plus f of 1 times 1 plus f of 2 times 1 plus dot, 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 plus f of 9 times 1. Now, under our new notation, I'm going to write this as sigma, can't write a sigma either, sigma from I equals 1 to 10 of f of x sub I, times delta x sub I. Okay, now, this is horrifyingly confusing, but I promise this and this are exactly the same thing, just with proper variables plugged in. This is simply the nicer way to write it, and this is a Riemann sum. Okay. Now, let's explain what this means. I'll write this out here. Okay. Now, the I means you iterate the sum, which just means you plug in I equals 1, then I equals 2, then I equals 3, then I equals 4, dot, 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 then I equals 10. Then take all the numbers, all those numbers, you get and you add them up. Okay. So what I have is what happened? What I have is I equals 1 to 10, f of xi times delta xi. So I have, this is exactly written as f of x sub 1 times delta x sub 1 plus f of x sub 2 times delta x sub 2 plus dot, 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 plus f of x sub 10 times delta x sub 10. Okay. When dealing with Riemann sums, this is your length or your height, and this is your width. So in our example, this is exactly equal to f of 0, because this is the first x value that we chose to define the function, or to define the rectangle, right? The first x value that we picked was 0, came up and drew a dot. The second one was 1, third one was 2, so on and so forth. And the width of each rectangle in this case, they're all the same, was 1. So the width of the first rectangle was 1. The height of the second rectangle was f of 1. The width, again, was 1. All the way up to the 10th rectangle, which, remember, because we chose left endpoints, the x sub 10, the 10th x value that we chose, was 9. And again, the width was 1. It's not always the case that these will all be the same in any given problem. But I think that in this class, we'll probably try to keep it that way, so that all of the intervals are divided evenly, meaning all of your rectangles have the same width. Okay. So how to say this? How do we say because I think this is important. I think it's often just assumed that you guys as students know how to say this, but I think it's important to emphasize it because I don't think it's obvious, and if you say it correctly, you'll begin to think about it correctly. So how do we say it? We say this exactly translates to the sum from 1 to 10 of f of xi times delta xi. Okay, so it's easy to say, oh, sum 10 to 1 because you're thinking maybe top down, but it's not. You want to think of I starts at the bottom and walks its way up these steps to the top to 10. This is how I think of this. I think this sort of looks like a staircase. So you're starting at the bottom and you climb your way up to the top. And this is where you stop. You're at the top of the stairs. You start at 1 and you end at 10 once you hit the top. Okay. All right, so in this example, we had x1 equals 1, x2, oh, I'm sorry, x1 equals 0, x2 equals 1, x3 equals 2, dot, 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 and x10 equals 9, right? So f of xi equals height or length of the ith, whatever I is, first, second, third rectangle. And delta xi equals the width of the ith rectangle, right? So all we're doing when I write this hideous looking thing is saying, all right, I goes from 1 to 10, so I have 10 rectangles that I have to add up the areas of. This guy gives me my height or my length, and this guy gives me my width. Width, length, and number of rectangles. Okay. Now this is not supposed to be clear the first time you see it, so you may have to watch that a few times to understand. And as always, feel free to come to office hours and ask questions. You'll only have homework problems based on this stuff, based on this lecture, this coming week. So um, make sure that you fully understand this, because it really is the only thing that we need out of you this week. Okay. So with all that said, we can rewrite the original problem. Saying the same exact thing, but with sort of better notation. So we have area under f of x is approximately the area of those rectangles. Which is equal to I equals 1 to 10, f of x sub I times delta x sub I. And all of a sudden, we look and feel much smarter and more efficient, right? Nothing wrong with feeling a little smart every now and then. Because if you show your parents a sum that looks like this, they're going to say, oh, yeah, okay, that's cute. I know how addition works. If you show them this, they're going to be pretty impressed, right? But they mean the same thing. And you know that, and they don't. And that makes you feel smart. Now let's look at a couple examples. And I might have bled into number 3 here. I'll try to make the timestamp match up a little bit. I didn't really have stopping points in my notes, so I apologize for that. But let's do a couple examples, just writing out, expand the following sums, right? This is just convert from sum notation into regular notation dealing with just pluses and not dealing with sigmas. So let's say we have something like a sum from I equals R to S, right? Whatever R and S are, it means absolutely nothing. The only thing you can assume from this is that S is bigger than R, because again, S is at the top of the staircase and R is at the bottom. And what's the function? It's just going to be f of I. So in this case, this is not a Riemann sum. This is not a height times a width. I mean, I guess you could assume that the width was 1 here, but it's not written in the form of a Riemann sum. It's a little different. This is just an arbitrary sum. Just getting us used to the notation. So what do? I plug in I equals R first, right? I start at the bottom number. I equals R, plug it in. I have f of R. Now I plug in I equals R plus 1. All right, that's f of R plus 1, right? Anywhere I see an I put an R plus 1. Then I plug in I equals R plus 2, f of R plus 2, dot, dot, dot. And the last one is I equals S, f of S. And I guess maybe I should write, just to be a little bit clearer here. Let's do one more. I equals S minus 1, and then I equals S. This is f of S minus 1, and then f of S, right? So I start at R. I go up by 1 each time. R plus 1, R plus 2, dot, dot, dot. I don't actually know how long this is because I don't know what R and S are. But then whenever I hit the end, it has to be S minus 1 and S. All right, so I have a sequence written out. And all I do is put pluses in between. Like this. Now I've expanded this sum to something that looks a little bit cleaner. Well, cleaner is not probably the right word. I think this is probably the cleaner way to write it. This is a little bit more of the more intuitive way to write it, I think. All right, let's try something a little more explicit. I equals 1 to 3, and we'll keep the same function f of I. All right, so I plug in the bottom number, f of 1, plug in the next number, which is 2, and then I plug in 3, and now I'm done because I've hit the top. So I put pluses in between, and I'm done. Okay, let's try something a little different. Let's try a different function this time. I equals 3 to 7. And let's say the inside of the sum is just I. It's not f of anything, it's just I itself. So this says, okay, take I equals 3 first, plug it in. And it spits out 3 because I'm just plugging in for I, and that's the whole function. Now I plug in 4, then 5, then 6, then 7. Once I hit 7, I stop. Plus, 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 plus. Remember, this is I equals 3, I equals 4, I equals 5. I hate this pen. I equals 6, and I equals 7. Okay, and one more. The sum from I equals 1 to 4 of 1 plus 3I squared. Okay, I start with I equals 1. I get 1 plus 3 times 1 squared plus 1 plus 3 times 2 squared plus 1 plus 3 times 3 squared plus 1 plus 3 times 4 squared. And I could expand this and simplify and so on and so forth, but I'm just showing this is how you expand everything. Okay. And, oh, sorry, one more. This one is a little bit trickier, I think, if you haven't seen something like it. So let's say I equals 1 to 5, and the inside is just 2. Now let's think about what this means. All I have to do, again, just like in any other case, is take I equals 1, plug it into the function. Okay, what is 2 equal to when I is equal to 1? Now up here in part C, when I is equal to 3, I is equal to 3. When I equals 4, I equals 4. When I equals 1, this function equals 1 plus 3 times 1 squared. But in this case, 2 doesn't depend on I. So when I equals 1, I just get 2. How about when I equals 2? It's still 2. It doesn't depend on I. And I continue to do this for each value of I. Right? Now, it's not as simple as just getting a 2 out. I have to get a copy of 2 for every new value of I. Right? I plug in I equals 1, I get a value. Plug in I equals 2, I get a value. Plug in I equals 3, get a value. I equals 4, I get a value, and I equals 5, I get a value. And now, and only now, do I stop. So I really get 5 copies of 2 here. Or 10. Okay. Now, there are some nice properties of this. Of this sigma notation. In particular, sums are what are called linear, which means that constants can be pulled out and constants is a very loose term here, right? Constant meaning something, really anything, actually, I should say. Anything not involving I. Okay, so that's important. Constants can be pulled out and sigma splits over addition. And this doesn't make much sense in terms of words, but I'll show you an example quick, just to show what I really mean by that. Okay. So let's look at the sum I equals 1 to 5 of 2I squared plus 2I over 3K minus 1. And actually, you know what? Let's get rid of K. Let's make that an N. It doesn't matter because it's, it's just any letter, but we'll use that. Okay. All right, so what do I mean by splits over addition? Well, here's what I mean. That the sum of a sum is the sum, oh, yeah, why am I writing 5? The sum of each individual piece. Oh, yeah, jeez. 1 to 5, right. And this is a negative 1 on the inside. This was a 2I over 3n on the inside, and this was 2I squared on the inside, right? I'll try to remember parentheses, but it should generally be clear that if it's only next to one term, it only applies to that one term. But I'll try to remember. Okay, so this is what I mean by splits over addition. That's this first step here. Anytime I have addition on the inside here, I can just write it as a sum of each individual piece. Okay, now by constants pulled out, I mean that anything not involving I can come outside the sum and multiply from the outside, right? Just like with a derivative, right? So I can pull the 2 outside, and now it's linked still by multiplication, but all I'm left with on the inside are I terms. And I can always do this, and this is important when we're doing examples later on. Now this, what is the thing that I can pull out? Well, again, anything not involving I can come outside the sum. So what in this case can come outside is 2 over 3n. And on the inside, I have I equals 1 to 5, and just I is left. And now in this case, I can pull a negative outside, pull a -1 outside. But remember, I still have this sum, and there's still a 1 in here, right? I can't pull anything out and be left with a 0. This sum never goes away. I'm always going to have a 1 living on the inside. But I can sort of pull out the negative to make anything in here positive. That can always happen. Okay, so now here's what I have, and I can write this sum out explicitly. Let's get the practice at least. So I'll put in brackets what this sum corresponds to. I equals 1 gives me 1 squared, and then plus 2 squared, plus 3 squared, plus 4 squared, plus 5 squared. Now I have plus 2 over 3 times n, and I do the same thing. 1 plus 2 plus 3 plus 4 plus 5. And I stop because 5 is at the top. And I just plug in the number itself because I'm just taking I equals 1, plugging it in for I. Minus 1 plus 1 plus 1 plus 1 plus 1, right? I have 5 copies of 1 because this is where I equals 1, dot, 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 I equals 5. Right? I'm plugging in I, and I get 1 each time. Okay, so what do I get out of this sum? Well, I'll simplify it a little bit. That ends up just being 55. You can check me on that if you like. This isn't the important part. We all know how to add and take squares. This is 15. Yeah, 15. And this is just 5. Okay, so I get 110 plus 10 over k. Yeah, 10 over 5. 10 over k. 10 over n, I'm sorry. My notes don't match. Minus 5. So it's just 105 plus 10 over n. And I could get a common denominator and rewrite that. But this is how you expand and compute a sum. And the sum becomes much easier when you can pull everything out that doesn't involve I. And that's a lesson that you're going to want to keep in mind when it comes later. Okay, so it appears I haven't overlapped with number 3. So we'll move on to number 3. And these are important sum formulas. What do I mean by this? Well, there are certain sums that we can find general forms for. So there was one example that we saw already. So the first one, we've sort of seen in action. And maybe this is the most obvious one. So if I have the sum as I goes from 1 to n of 1, remember I plug in I equals 1, and when I plug in I equals 1, I get 1. When I plug in I equals 2, I get 1. So on and so forth, right? Plus dot, 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 all the way up until I equals n, and I stop, right? In this case, I just have a general upper bound because I don't want to make it too specialized. I don't want to make this, 5 or 10 or something like that. I want it to be able to be any number and find sort of a general formula. So I have n copies of 1. Here's the first one. Here's the second one. Dot, dot, dot. Here's the nth one. Okay, so it should be a little obvious that this is n times 1, or just n. So this is your first formula, that the sum from 1 to n of 1 is equal to n, meaning just whatever the upper bound is. Okay, so now the second one has a little bit of a story to it. So let's take the sum I equals 1 to n of I. So in this case, when I equals 1, I have 1. When I equals 2, I have 2. When I equals 3, I have 3, so on and so forth, all the way up until I equals n. And of course, in that case, I get n, right? Wherever n is, wherever the stopping point is. Okay, so what is this equal to? And to answer that, I want to tell you about a guy named Carl Friedrich Gauss. He is pretty much the smartest guy to ever exist, one of the greatest mathematicians of all time. And just one of the examples of his brilliance is when he was in elementary school. Now, you'll hear people tell this story, and he seems to get younger every time you hear the story, but he was in first grade or kindergarten or something like that. And his teacher was annoyed with the class. And he said, okay, here's an assignment to shut you up and, get you off of my nerves. Add up assignment. Add up all numbers from 1 to 100, which is exactly what we're doing here. If n equals 100, I'm adding up 1 plus 2 plus 3, dot, 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 plus 99 plus 100, right? So this is just one of the special cases. So Gauss, in first grade, or whatever grade he was in, right? Some sort of elementary school, whatever. He was young, right? Way too young to be able to figure this out. Gauss had the answer in less than 2 minutes. And of course, for a first grader to do this is, obscene, especially in less than 2 minutes. So when he gave the answer, the teacher checked and it was correct. And he said, how did you do it? Well, he said, list all the numbers from 1 to 100, or from 1 to 50. So go up halfway, right? And you can write them all out, or, it's easy to see the argument if you just have dots here, it's fine. List all the numbers from 1 to 50. Now below that, in opposite order, list all the numbers from 51 to 100, right? There's 50 numbers from 1 to 50. There's 50 numbers from 51 to 100. This is 90. 98, 99, and 100. Okay. And he said, all right, I want to add all these up. Okay. And I can add in any order I like. So let's add down. Let's take this list of numbers and add down pairwise like this, right? So I get 101, 2 plus 99. Oh, that's also 101. And I'll put a plus in between here because I want to add these things up, right? Because there should be pluses in here. I get another 101, 101, 101, 101. Okay, well, this is just 50 copies of 101. 1, 2, 3, dot, 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 48, 49, and 50. Okay, so this is 50 times 101. Or in general, 100 divided by 2 times 101. Okay, this is the easy way to do it. And this is the way that Gauss found. And in general, this formula works. So in general, the formula n times n plus 1 over 2 works. So this thing is equal to n times n plus 1 over 2. And a first grader figured that out, which is pretty cool, if you ask me. Okay, and then there's one more, which I definitely don't typically have memorized. Every time I teach this class, I sort of rememorize it, but then I forget it by the next time I teach it. But this one is the only other one you'll have to know. And it is the sum of the squared numbers. So this is 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared. And this is equal to n times n plus 1 times 2n plus 1 divided by 6. So sort of similar to the one before, to the n times n plus 1 over 2, but you have this extra 2n plus 1, and you have an extra 3 on the bottom. I'm sure there's a nice way to remember that as well, but I don't really have one available to me. So this is just something else you have to memorize. So now, 1, 2, and 3 are the important formulas, and these are all you're ever going to have to know to solve any problem involving a sum, in this class at least. Now that we have the formulas, let's take a look at some examples and use them. So let's look at the sum of I equals 1 to n of the function 4i squared plus 10i plus 100. All right, so we use linearity just as we did before because we want to break it down to look like one of our formulas, 1, 2, or 3. So in every one of these cases, I have to make this whole thing decompose into these formulas because otherwise I don't know what the sum is. So using linearity, I can split the sums. And then using the other property of linearity, I can pull constants out, right? Anything that doesn't have to do with an I comes out of the sum because only then can I substitute in the formulas that I have. Okay, so let's note, when I use these formulas, one through 3, I am evaluating the sum. That means I'm taking a bunch of things added together and I'm telling you what it equals, right? So I have this notation here means that I have n terms in my sum, one thing plus another thing plus another thing, so on and so forth. And I'm saying that this whole thing is equal to just this. So in particular, sigma goes away. Just like a limit or derivative, right? When I take a derivative, d dx of x squared, I don't write d dx of 2x, right? Instead, I just write 2x because I'm evaluating this ddx. This tells me that I have to evaluate something. It's the same way for a sum. So when I go to plug in, I have 4 times this thing, n times n plus 1 times 2n plus 1. Because I know what this is, I have a formula for it. I also know what this is, I have a formula for it. And I know what this is because I have a formula for it. Once I'm at this place, then I can plug in the formulas. But before then, it's all linearity. Plus 10 times the formula that Gauss had, n times n plus 1 over 2, plus 100 times n, right? This is just n because it's n copies of 1. All right, and I guess we can simplify a little bit. 4 over 6 gives me 2 over 3. So I get 2n times n plus 1 times 2n plus 1 over 3 plus 5n times n plus 1 plus 100n. And for the time being, we'll just leave this as it is. We'll be doing more simplification and stuff later. Okay. So that does it for section 3. Let's move on to section 4. And I don't remember what I called it, but return to calculating area. So we're going to return to the examples that we had seen and recall that we said we could use left or right endpoints to define our rectangles, right? So we're just returning to the point where we use rectangles to estimate area. For some estimates, we could use left endpoints. For some, we could use right. It's up to us. When it comes to defining the integral, it doesn't matter. However, when it comes to using Riemann sums to approximate integrals, so when it comes to integrals, which we haven't defined yet, so don't worry too much about that. It doesn't matter. It doesn't make a difference whether we choose left or right endpoints. But just as if we would ask you to compute average velocity in the derivative case, when it comes to approximating integrals, approximating area under a curve, which we would certainly ask you to do. There are definitely problems like this, similar to calculating average velocity. It does matter. We have different formulas for each. Okay, so these are just things to note. All right, so let's look at now an example where we have to use Riemann sums to approximate the area under a curve. Approximate the area under the curve f of x equals x squared on the interval 0 to 1 with n equals 4 rectangles. And we'll do it using A left endpoints, sometimes called the left rectangle method, and B, right endpoints, sometimes called the right rectangle method, just for short. Okay, so let's work through this, and I'll try to come up with a nice list of steps that we can follow. So the first thing you should do is give a graph of the function on the interval that you care about. So in this case, I have 0 to 1, and we're going to drop a bar, or at least draw a bar from 1 up to the function, right? So this is the shape, this little rounded triangle shape that I'm trying to find the area of, okay? And this is f of x, right? This is just x squared. It's a parabola. Of course, it would be symmetric over here, but we don't care about anything less than 0. We're just looking at 0 to 1. Okay, so first thing I should do is divide the interval 0 to 1 into n equals 4 equal subintervals. Okay, so let's do that, and we'll do it on the picture. So it looks like one of them will be here, one of them will be here, and one of them will be here. This is 1/4, 1/2, and 3/4. Okay, probably should have made my picture a little bit better, but that's fine. Step 2, draw your rectangles. All right, so I'm defining these by left endpoints for part A. So let's just do the LRM first, and then we'll come back and we'll deal with part B separately. Okay, so this, remember, says that the height of the rectangle is determined by the left endpoint of the rectangle. So notice I have 4 rectangles here. One has width 0 to 1/4, another has width 1/4 to 1/2, another has width 1/2 to 3/4, and the final one has width 3/4 to 1. There are 4 even rectangles that can be constructed in here. So the left endpoint of the 0 to 1/4 is right here. And here's where the function is. So the height, it turns out, is 0 in this case. So I don't really have a rectangle. It's just sort of a horizontal line. There's nothing there. Okay. In this case, f of 1/4 is right around here. So I draw a straight line over, and then I drop it at the next interval. At 1/2, this is the next left endpoint I have. I come up, here's f of 1/2. I just go straight above 1/2 and construct the rectangle. And at 3/4, I'm up here and I construct the rectangle. And of course, this is the last one because this is the last left endpoint that I have. And now I'm looking to find the area of these rectangles. And this should provide me an estimate, not a very good estimate, but an estimate of the area under this curve, this weird triangle looking shape here. Okay, so now part 3, or step 3, is to write the Riemann sum. Form or formula, I guess. What I mean is the area, and I'll write sub L to mean using left endpoints, is I equals 1 to n, where n is the number of rectangles. So 4 in this case, 4, again, coming from this. And then I have my f of xi just as we had before, but I'll put an L up here just to remind ourselves again that we're doing left endpoints, right? The L doesn't mean anything except left endpoints. Delta x, and you know what? And I'm not even going to use delta xi. And the reason is all rectangles have same width, right? Remember that delta x stands for the width of the rectangles. Because I've divided them into equal subintervals, they're all of the same length, or all the same width in this case. And in this particular case, it's 1/4, okay? All right. So now my next step is to find the width of each rectangle. And we've already done that. And it should be obvious from the picture. In this case, this is, well, in symbols, this is delta x. And in this case, each rectangle is 1/4 wide. How do we find this in general? In general, take the length of the interval and divide it by n, right? I take the length of the interval, however long my thing is, and then divide it by the number of rectangles. I'm evenly distributing the rectangles. This is what division is used for, right? So in general, it's b minus a over n, if I'm given an interval a to b. So for interval a to b. In this case, we have 1 to 0. So I just have 1 minus 0 over a fourth, or over 4. 1 minus 0 over 4 equals delta x. So 1/4 is what I plug in for delta x. Great. Okay. Next, I want to list the special x values. And what do I mean by that? These are the XILs. Okay, so what I'm looking for are the left endpoints of the rectangles, right? Just the x coordinate of them, though, right? So the first one I did was x equals 0, then 1/4, then 1/2, and then 3/4. So in this case, I have the first one, right? This denotes which number rectangle I'm looking at, right? Because I goes from 1 to 4. There's 4 rectangles. This horizontal line is the first one. Here's the second, third, and fourth. So the first rectangle has left endpoint 0. Second has 1/4. Third has 1/2. And fourth has 3/4. Right? x1, x2, x3, and x4. Of course, we don't count 1 because, first of all, we only want 4 rectangles. And second of all, 1 is not a left endpoint. We'll deal with 1 when we deal with right endpoints, but for right now, we're doing the left side. So we only have these 4 values. Great. Okay, so now we move on to evaluate all the f of xil. Evaluate all of these things. What I mean is just plug in the special x values. Right? So f of x1 is f of 0. And this is, remember that our function was x squared. So this is just equal to 0. And then we have f of 1/4. That's 1/16. F of 1/2 is 1/4. And f of 3/4 is 9/16. Okay. And now finally, I guess I could do it over here. Step 8 is to, oh, what did I do? Oh, I didn't mean to write that. I'm sorry. Counting too much here. That should be 6. Right, step 6. Step 6. Come on, there we go. And then step 7 is plug everything in to the Riemann sum. That's an N. Terrible handwriting. To the Riemann sum, right? We have the formula. This is I equals 1 to 4 of f of xi L times delta x. And now we know what f of xil is for each I, and we know what delta x is. Okay, so expanding this out gives me the sum, right? This is me just expanding the sum. Right? I equals 1, I equals 2, I equals 3, I equals 4. x1, well, I know what f of x1 is, actually. So I get f of x1 is 0, so I get 0 times, what's delta x? Delta x in this case was, what, 1/4, right? Plus x2, f of x2 was 1/16 times 1/4. This should be delta x plus 1/4 times 1/4 plus, finally, 9/16 times 1/4. I can factor out a 1/4 here. I get 1/16 plus 1/4 plus 9/16. And in general, this here is delta x. I can always factor this out, no matter what. So I could have factored it out right to begin with. And this makes sense, right? Because delta x doesn't have an I in it. This, of course, I can't factor out because there's an I in the subscript. It depends on I. But delta x does not depend on I. All the rectangles are the same length. I can factor this out of the sum, just as I'm doing here, right? This is always allowed to happen. Okay, so this ends up being 1/4 times, what does the inside turn into? I have it written down here. 30/16. And you can convince yourselves of that. And this turns into 15/32. So this is an estimate of the area under f of x from, on, I should say on, f of x on 0 to 1. Okay, now let's do the same thing for b. I'll move a little bit faster through this one, though. Let's construct a new picture. New estimate, new picture. That's a good rule. New estimate, new picture. So we have this same function. Here's 1, give myself a little bit more room this time. And here's 0. Okay, we divide again into even subintervals. Okay, 1/4, 1/2, and 3/4. Everything stays the same here, except now, let me just remind ourselves, n equals 4 even rectangles. I'm going to have 4 of them. Step 2 was to draw the rectangles. Okay. Now, because we're doing B, the right rectangle method, I start at the right end of every rectangle. Remember, I have a rectangle between 0 and 1/4, 1/4 and 1/2, 1/2 and 3/4, and 3/4 and 1. But in this case, instead of using 0, I'm going to use 1/4 and draw my horizontal line to the left. So now I have a rectangle which is above the function. So I'm going to have an overestimate in this case. And in this case, I have 1/2 as the right endpoint of the next one, 3/4 as the right endpoint of the third rectangle, and 1 as the right endpoint of the fourth rectangle. And I'm looking for the area of this thing. Right? And this will give me an estimate. So I have step 3, area sub r, meaning right endpoints, is again approximately the sum I equals 1 to 4 of f of x sub I, but I'm going to put an r up here because now we're using right endpoints, times delta x. Okay, and again, remember I can always pull out my delta x, so I can rewrite it like this. Equals 4, I equals 1 to 4. 1 to 4 of f of x sub I r. Okay, so 4, I need to find my delta x. Delta x equals 1 minus 0 over 4. This is still 1/4. So this doesn't change with L or R, meaning I can use left or right endpoints and I still get the same delta x. 5, I need to find x1 sub r, and in this case, I used 1/4. x2 r is 1/2. x3 r is 3/4, and x4 r is 1. Okay, so now step 6 is evaluating each of these. So f of 1/4 is 1 over 16. F of 1/2 is 1 over 4. F of 3/4 is 9 over 16. And f of 1 is 1 squared, which is just 1. Okay, and now I have step 7. I plug everything into the formula. Sum from 1 to 4. Crap, I should have my delta x on the outside. That's probably better. So my delta x is still on the outside, and I have the sum I equals 1 to 4 of f of x I super r. This is equal to delta x, I know, and that's 1/4. And now I have the sum of all of my f values. So I have 1 over 16 plus 1 over 4 plus 9 over 16 plus 1. Okay, simplifying this, just get a common denominator and you find out what it is. It ends up being, oh, I'm sorry, I made a mistake here. This one is 30 over 16. I apologize. I'm going to go back and change that. This should be, I was reading the wrong example. Sorry about that. So get rid of this and get rid of this. Okay. This should be 7 over 32. Sorry about that. I should have double checked myself. Nope, again, screwing up. That's the answer. What I really want is 14 over 16. That's right. 14 over 16, and this is 7 over 32. Sorry about that. Okay, so this is 30 over 16. I multiply it by 1/4, and I get 15 over 32. And remember, this is approximately area under f of x on x on 0 to 1. Great. Okay. So this is fine. This is certainly a way to do it. But a lot of times we want general formulas. So if you prefer general formulas, we have the following. The area using right endpoints can be approximated by the following. Let's work through it. I equals 1 to n of f of xi to the r delta x. So remember, we can pull delta x outside. I equals 1 to n f of xi r, right? And notice this r doesn't mean an exponent. This just means it's right. It's just another way to denote it. So don't think that I'm raising x to the r or anything like that. It's just another index that I'm using. Okay, but remember, delta x equals b minus a over n, right? We said that already. So I can replace that in the formula. Okay, that's a little bit better because now I don't have to find delta x. I removed that step from my problem. And next, let's return to the example that we had of x squared, and let's think about it for a second. So we'll do the interval from 0 to 1 again, and I'll do 4 even subintervals. And they're not quite even, but fine, good enough. Now, notice that, remember, delta x is my width, right? So this thing has length delta x. And so does this thing. And so does this thing. Even though it doesn't look like it. But these are all even length. They're all equal to delta x. So when I'm using right endpoints, how can I find a nice formula to write xir and sort of get rid of this crappy notation and involve just i's, n's, a's, and b's? Because this is the information that I'm given right in the problem, right? I is easy because that's just the thing that plugs into the sum. N is easy because that's given. We're asked to calculate using a certain number of rectangles. And A and B is the interval that we're given. So how do we find out what the right endpoints are? Well, what if we start at the left endpoint, which is A, right? And 1 in this case is equal to B. And to find the first endpoint using the right method, I just start at A and add 1 copy of delta x, meaning I take A and I add delta x. So x1r is A plus delta x, right? That's how I get from 0 to 1/4. I just add a delta x. How about for the second one? Well, instead of adding 1, I just add 2. So I start at A and I add 2 copies of delta x, A plus 2 delta x. Now, how about the third one? Okay, maybe you've seen the pattern already. 1, 2, 3. A plus 3 times delta x, right? I add a plus delta x plus delta x plus delta x. And that gets me to x3. Okay, now how about x4? A plus 4 delta x. So in general, what if I say x sub I? What does that have to be? Well, notice that this number is always the same as this number. So whatever number I plug in on the bottom, I get it next to delta x. And a always stays the same. So this is a plus I delta x. Oh, and would you look at that? I know what delta x is too. A plus I times b minus a over n. And all of a sudden, I've gotten rid of delta x's and xir and this hideous notation. It's a little bit nastier looking algebraically, but all of the information that we need is given to us in the problem. It's just a matter of plug and chug at that point. So using all that, I can rewrite my formula one final time as I equals 1 to n times this delta x of f of this new version of xir, a plus I times b minus a over n. And this is my new right rectangle estimate, my new RRM formula. And this is something you can absolutely memorize. It's helpful to know the intuition behind it, though, because this is not something that's terribly easy to memorize, at least for me. If you're good at memorization, great, just memorize it. You don't really have to know what's going on in this case. But for me, having this sort of a picture and understanding this idea here helps me a lot to keep this straight in my head. Okay, and now it's even different when I use left estimates. So the area using left estimates can be approximated similarly, except there's a very, very, very subtle difference, and it's frustratingly subtle. So I still have my delta x here, right? This is still delta x. And I still have my f of a plus I b minus a over n on the inside. So this is still height, right? And I still have just as before, I still have this sort of a formula, except now it's a little weirder. So let's look at the first guy that occurs when I use the left endpoints. So here, I'm starting at A, and I'm not moving any copies of delta x. Right? I'm starting at A and I'm not moving, right? This is my first endpoint, and I draw my bar straight over. So this is equal to 0, which is just equal to A, right? So how about x2 of L? Well, now that's equal to A plus delta x. Okay. How about this? Well, this is A plus 2 delta x, right? To get to the second one, I add 1 copy of delta x. To get to the third left endpoint, I go 1, 2. Now I'm there. Now to get to the fourth, remember our fourth started at 3/4, so it was 1, 2, 3. I start at A and I add 3 copies. So now let's think about this. It looks like I can write this way, right? 0 copies of delta x. It looks like whatever number I have down here is always going to be 1 bigger than what I get up here, right? I'll put a 1 in there so it doesn't look like a 0. Get a 4, I get a 3. Okay, so when I plug in I get a plus I minus 1 delta x. Now I guess I could write this in that way. I could replace I with I minus 1. But it's actually easier if you just shift these indices here. So instead, I'm going to write I equals 0 to n minus 1. So instead of starting at 1, I can start this counter wherever I want it to be. So let's start it at 0. So for the first term, I equals 0. So this can be written as a plus I delta x. So the first term, instead, this is now the 0th rectangle. And this is the first rectangle. This is the second rectangle. This is the third rectangle. So I start my numbering, change numbering from 1, 2, 3, 4 to 0, 1, 2, 3. It's just a change in numbering, and I think doing it this way rather than replacing this with an I minus 1 is a little bit easier. However, this is certainly the more confusing version. And because of this, when we do integration, we're going to use the right-hand side estimates, just because starting our numbering at 1 makes a little bit more sense. But you need to know this to estimate using left endpoints. But you only need to use it for estimation. You don't need it when you're actually computing the actual area. And you'll see that again in a little bit when we define the integral. Okay, let's do some examples. Let's stop talking about that stuff and actually get our hands dirty with it. So find the easy one in this case, find the right Riemann sum. So this isn't even asking us to evaluate it, just to find it. For f of x equals x cubed on the interval, what is it, 2 to 8, with 3 rectangles. Okay, so we recall our estimate for the area using right rectangles, that our formula is b minus a over n times the sum from I equals 1 to n of f of a plus I times b minus a over n. This is something you just have to have memorized. But of course, it's easier to memorize when you know the picture. Okay, now let's start plugging stuff in. A is 2 and b is 8. So I have 8 minus 2 over 3 times the sum I equals 1, n equals 3. So I have 3 as my stopping point. F of 2 plus I times 8 minus 2 over 3. All right, we can simplify a little bit. 8 minus 2 is 6. 6 divided by 3 is 2. I equals 1 to 3. F of 2 plus, remember 8 minus 2 is 6. 6 divided by 3 is 2. So I get 2 plus 2i. And now finally our last step is to get rid of the f, right, to plug this in for x in the function. We just get 2 plus 2i cubed. And in this case, we're done. This is the right Riemann sum for this function on this interval with this many rectangles. Okay, how about another one? But this time, let's do the left. F of x equals ln of x on the interval 5 to 7 with 4 rectangles. Okay, so remember the formula? I have b minus a over n times the sum. Now I starts at 0 because I'm using left to n minus 1 of f of a plus I times b minus a over n. And I start plugging in. Okay, so I have b minus a is 7 minus 5 over 4. And then I have the sum I equals 0 to n minus 1, which is 3. F of 5 plus I times 7 minus 5 over 4. Okay, 7 minus 5 is 2. 2 over 4 is 1/2. Basic math, Nick. I equals 0 to, not n minus 1, it's 3. I know what n is. And I have f of 5 plus 1/2 I, or 5 plus I over 2, I guess. Right? Okay, so I get 1/2 times the sum I equals 0 to 3 of this thing plugged into ln of x. ln of 5 plus I over 2. And this is what I have. Okay. So we've found left and right Riemann sums for various functions. Okay. Now, let's get to the thing that we've all been waiting for. I think this is number 4. God, I don't remember. Maybe this is number 5. I think it's number 5, actually. Defining integrals. Let's define an integral. But first, let's return to motivating example. Okay. So I have this thing, this wavy looking thing on the interval 0 to 10. And I'm going to call this f of x. Okay, so with the knowledge, we now have we can estimate the area under f of x on 0 to 10, on the interval 0 to 10, with n rectangles, as many rectangles as you want, right? We can just pick. We know how to deal with it no matter what n is. So we know how to estimate it using left Riemann sums. We end up getting 10 over n, I equals 0 to n minus 1 of f of 0 plus 10i over n. And we know what the right one is. It's the same exact thing, except the indices on the sum are shifted. Right. Okay. However, this is still just an estimate. Right? This isn't good enough. How can we get the exact area? Right? We're still in search of what is the area under this function. We still haven't answered that question. With all the work that we've put in, we have not answered the question. So we noted before that the more rectangles we took, the better the estimate. Right? Recall that. So basically, we tried to color in the shape but we missed some spots and colored outside the line a bit. Right, this is basically what happened, right? We tried to throw some rectangles in here, and no matter how many rectangles we get in here, we're always going to sort of be missing stuff, or we're going to get some extra stuff, right? So let's try it with just a bunch of rectangles, and we'll see at least that we're getting closer, right? Let's take, I don't know, just a ton of integrals here. And I'll probably cut this out, me constructing these integrals. I'll do it on the right-hand side, and then it'll just jump ahead to when I'm finished with it. Okay, so now looking at this big mess of a picture. Notice I still have these little pockets here that I haven't colored in yet. And then on top of it, I have this stuff up here, which I colored in too much of, right? I've colored outside the lines here. And then I have this big pocket here missing, right? It's still an estimate, but it's definitely getting better, right? The smaller I make these rectangles, the less mistakes that I make, right? Smaller the rectangles, less mistakes I make. And small rectangles means more rectangles. Right? The smaller I make these, the more I have to fill in this entire interval, right? Okay, so wouldn't it make sense to have infinitely many rectangles? Then I could take my shape and color it in basically just by vertical lines, right? And all of these, because they're infinitely close, are just going to start getting filled in. And notice the more vertical lines I draw, I really have this section colored in. Now imagine that takes part throughout the whole thing. If I have infinitely many rectangles, that means they're infinitely small, right? So it seems like this is the answer, right? Now remember, when we're saying this, n is the number of rectangles. So let's let n go to infinity. And how do we deal with stuff going to infinity? That's exactly right. Limits. What we do is we take our estimate and we take his limit. So the area under f is exactly, no longer an estimate, the limit as n goes to infinity of exactly the formula that we had. Now notice I don't need, it doesn't matter whether I use left or right endpoints, because if the rectangles are infinitely small, you can really just think of the left and right endpoints as being the same thing, right? If it's just a vertical line, the left and right are the same thing. They've sort of collapsed onto one point, right? So let's use the easier one. Let's use the one that we're more comfortable with. The one that starts with 1 in particular, the right endpoints. And the area under f of x is exactly this thing. We call this the integral of f of x from a to b with respect to x. Just like in derivatives, we have to make specific what the variable is. So there's going to be x's floating around when you're dealing with a function. So we have to just say with respect to x. So it's, it's like a dy dx. The dx part means with respect to x. And we use the same notation here. And we write, so this is the notation, the integral from a to b of f of x with respect to x. And this is exactly what I have above. I'll just write it again so I can box it and star it. This is your definition of the integral. And this is something that you have to have memorized, just as when you memorized the definition of the derivative, right? So this is super duper important. And that's what we have. Now, in terms of the notation, how I think of this symbol here is over here. Remember, when I was dealing with sums and stuff, I was dealing with sort of discrete jumps. It was like rectangles. I was moving one jump at a time like this, right? As I climbs, he jumps one number at a time. I equals 1, I equals 2, I equals 3, all the way up to n. And I'm jumping sort of over these rectangles Over here, this is like a smoother S. And I think of it as just one continuous line of where I'm not really jumping from rectangle to rectangle because they're all sort of right on top of each other. So I think of this as like a smoothing out. This is just a regular old S, and it's a lot smoother than this staircase looking thing. That's just, I don't know, that's a cool way to think of it for me. This exactly corresponds to delta x, right? Just like when we took a derivative, we had delta y over delta x and turned into dy dx. Same thing here. F of x is exactly the same. It's just, we're able to write f of x instead of this big nonsense. And again, the s corresponds to this, and a to b encodes the interval that we're interested in. Okay. Last but not least, let's start computing some integrals. And let's do the mountain of work that is required for these things, because there is quite a lot. All right, so evaluate the integral from -2 to 6 of the function 3x minus 1 dx using the definition of the integral. So this should sort of start ringing some bells. Remember how we said evaluate the derivative of this function using the definition of the derivative? This is exactly the same way. The light at the end of the tunnel is that next week, the lectures will all be based on shortcuts, like those derivative rules that we had. We're going to have integral rules as well, and there's going to be shortcuts to compute these. But for right now, this is all we have. And you'll see why we came up with shortcuts, and you'll see why the fundamental theorem of calculus is so important. Okay, so let's do this in steps again. Let me organize this a little bit. So steps to solving these problems, because they're a little bit lengthy. First, find the important info. Right? I need to know what A is because I need to plug that into the formula. A equals -2. A is the bottom guy, right? I start at A and I go up to B in a similar way that I started at 1 and went up to n when I was dealing with a sum. B is 6. It's the top bound. And f of x is this thing in parentheses, the thing that I'm integrating. 3x minus 1. Great. Next, write the integral definition. Okay, so just translate this into the sum version, or the limit version. B minus A is 6 minus -2 over n. And in this case, we're not given a number of integrals or a number of rectangles because we're pushing that number to infinity. That's the whole point of the integral. So you're not going to be given a number of rectangles here because we're not estimating anymore. We're finding the exact answer. So essentially, n is going to act like infinity here. And we're going to keep this limit to keep track of that information. It's important that you do not drop this limit. I can't emphasize that enough. This needs to carry through. Otherwise, you're just taking an estimate. Pushing the limit is exactly what makes the integral the integral. It makes it the exact answer. I equals 1 to n. Nothing changes here. This is always 1 to n. And now I have f of a, which is -2, plus I times b minus a over n. Put that in big brackets. And we simplify. 6 minus -2 is 8. So I get 8 over n. times the sum I equals 1 to n of f of -2 plus 8I over n. Okay, and the last thing to do is, well, I know what f of x is, so I just plug this thing in for x. I'm just trying to get this into something that I can work with. So I have 3 times -2 plus 8I over n minus 1. And I'll put this whole thing in parentheses to denote that I'm taking the sum of this whole thing. I can't lose any part of that. Great. Okay. Now, once I've done that, we just keep simplifying. So how do I want to say this? Let's just say I guess simplify. Yeah, simplify further, I guess would probably be the best way to say that. Okay, so let's make this look a little bit better. 8 over n has to stay. Let me just write what I have so I don't lose it. Limit as n goes to infinity. 8 over n, I equals 1 to n. Three times -2 plus 8I over n minus 1. Great. Okay. Do a bit of algebra on this. Get 8 over n. And I get a -6 plus 24I over n minus 1. Okay. One more little thing. Just to combine the like terms inside the sum. And I get -7 plus 24I over n. Great. Okay. All I've done is simplify the summand. This is what this is called, the summand, the thing inside the sum. Step 4. Use linearity to solve the sum. Solve, probably evaluate would be better. Evaluate the sum. What I mean by that is keep the limit. Keep the 8 over n on outside. That's not going to change. This 8 over n is going to stay here until we take the limit. Well, until we distribute it in and then take the limit, I guess. That'll be one of the last steps. So now I'm going to have this 8 over n times a big quantity. And here I'm just going to work with the sum. Okay, so I have a -7 on the inside of this sum, plus, using linearity, I equals 1 to n, 24I over n. I'll put parentheses around that. Big parentheses to tell me that 8n has to distribute through, right? 8n has to apply to this whole sum. So when I break it up, it has to apply to both pieces. And then a final bracket to remind me that I'm taking the limit of this whole thing. Okay, so I still have a couple things to do. I still have to pull out anything that isn't an I from the sums, keeping all my parentheses. So let's pull out the -7. And I'm left with just 1. Remember, this doesn't go to 0. I'm left with a 1 when I pull out a -7. -7 times 1 is -7. -7 times 0 is 0. And here, 24 over n can be pulled out because this, even though there's an n in the bounds, this doesn't have anything to do with n. All this says is that n is the stopping point for I. The only thing that has to stay inside the sum is I. So I pull this out, and I'm left with just an I on the inside. Big parentheses to remind myself that 8 has to distribute, 8 over n has to distribute, and big bracket to remind myself that I'm taking the limit. Okay, now that I have this, I'm at the point where I can apply my formulas. So this is step 5, apply sum formulas. Okay, so I still have equals limit as n goes to infinity. Big bracket, 8 over n. Now I have the sum from 1 to n of 1. I know what that is by my formula. I have -7 times n. Right? Remember, a sum from 1 to n of 1 is just n. It's whatever the top bound is. Plus 24 over n, and this is the one that comes from Gauss. The sum from 1 to n of I, 1 plus 2 plus 3 plus 4, dot, 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 up to n, is n times n plus 1 over 2. And I put a big parentheses to remind myself that 8 over n distributes, and a big bracket to evaluate the limit with. Okay. Step 6, reduce fractions where possible. So this is now all algebra from this point up until I plug in the limit. So I want to get this to be a form that I can work with, because right now if I plug in n goes to infinity, I have something over infinity, which this is going to be 0, plus something which looks like goes to infinity. So this is an indeterminate form, in fact. This is 0 times infinity. But there's some simplification I can do in here. So let's work with that. Limit as n goes to infinity, big bracket. And let's simplify the thing inside the soft parentheses here first. Let's not deal with the 8 over n quite yet. I get -7n plus 24 over 2 reduces to be 12. This n and this n cancel. So I just get 12 times n plus 1. Okay, it's already looking better. Now let's distribute the 12 through the n plus 1 and combine like terms. So I'll do that in one step. Still have the 8 over n outside, still have my limit, still have my parentheses. I had a -7n and a positive 12n. So that corresponds to 5n. And I just had a plus 12 as well. Like this. Finally, distribute the 8 over n. This is 8 times 5 is 40, and the n's are going to cancel in this case. So I get 40 plus 8 times 12 is 96, so I get 96 over n. Finally, this is something I can work with in terms of a limit. So step 7 is finally evaluate the limit. So I plug in n equals infinity, and I get 40 plus 96 over infinity. Notice this goes to 0, right? Just by problems we've done in the past, right? A fixed number over something going to infinity is 0. So in this case, the integral is equal to 40. Okay. Now, let's try one more, and I'll be a little less explicit with the steps that I'm doing. I'll just sort of do it all in one. But it's a little bit more complicated, this one. So just bear with me and rewind the video if it ever becomes unclear, and feel free to ask questions. So we want to evaluate the integral of x squared with respect to x using the definition of the integral. Okay, so important information. A equals 3, b equals 7, and f of x equals x squared. All right, so writing out my definition, this integral is equal to the limit as n goes to infinity of b minus a is 4 over n times the sum I equals 1 to n of f of 3 plus 4i over n, right? 4 over n is my delta x, and I multiply that by I. Great. So now I have limit. I certainly keep writing that. And it is 100% guaranteed that every time you stop writing a limit in these sorts of problems, no matter how many problems there are, we will take a point off, because it is super duper important that you carry the limit through and that you evaluate it at the end. So plugging 3 plus 4i over n into the function, I get 3 plus 4i over n squared. Okay, there's a bit of algebra there to do, but that's fine. Don't panic. I can handle this. I equals 1 to n. Squaring that thing out gives me a 9. I'll put this in parentheses. Plus 3 times 4 is 12, and I get 2 copies of that. So I get 24i over n. And then I square the last term, 16i squared over n squared. Okay, good. All right, let's continue to simplify. So I got a 9 here plus a 24i over n here plus a 16i squared over n squared. Close those parentheses and close that. All right. What's next? Let's apply linearity again. And in this instance, we're pulling constants out. So I have big parentheses, 9 times the sum I equals 1 to n of 1 plus 24 over n. Those are all the things that don't have anything to do with I. I plus 16 over n squared and I squared on the inside. Okay, so it looks like I'm going to have to use the I squared formula, which, all right, that's not great news, but at least I've gotten down to the point where I can get rid of these sigmas, because they're sort of cluttering up my work and they're confusing. They're horrible to look at. So let's plug in. I'm going to see if I can fit this on this line. I think I can. 4 over n times 9 times this thing, which you should have memorized, n, plus 24 over n, which if a first grader can get it, you should be able to have it at least memorized. And this one, you're slightly excused for not having memorized. But I would try to nonetheless, because it'll make your life easier. 6, close this, close one more set, and close the brackets. Okay. Now it's a simplification game until we can evaluate the limit. All right, so I'll leave the 4 over n on the outside. And on the inside, I'll have a 9n plus 24 over 2 reduces to 12. This n cancels with this n. So this becomes a 12. 16 over 6 becomes 8 over 3. Divide both by 2. One of these ends cancels. All right, that makes my life a little bit easier. So I have a 9n, a 12n plus 1, plus 8 times n plus 1 times 2n plus 1 over 3n. All right, not too bad. Let's distribute everything through except for the 4 over n. So I have 9n plus 12n, which is going to give me 21n, I believe. Let me double check and make sure I'm still on the right track here. Yep, this looks right. Okay, so I have 21n plus 12. Right, I get a 12 out of this as well. Plus, now this is 8 times 2n squared plus, I get an n, I get a 2n, so I get plus 3n plus 1 all over 3n. Okay. Still have my 4 over n on the outside, still carrying my limit through. And let's distribute that thing through 21 over n, or 21 times n plus 12 plus 16n squared plus 24n plus 8 over 3n. Now, here's something that didn't happen last time. And this is something that you probably should be able to do, but maybe it's not obvious right off the bat. 21n plus 12 plus. Now, I can split this fraction up to be 16n squared over 3n plus 24n over 8 over 3n and plus 8 over 3n. So what I mean is I have 16n squared over 3n plus 24n over 3n plus 8 over 3n, right? I can do this. This shouldn't be new. And I can write it as, I'll have to jump onto a new page, which is unfortunate, but it's fine. This can reduce. I get 16 over 3n, n on top, so I should probably rewrite that. 16n over 3 plus 24 over 3 is 8. The n's cancel, so I just get 8 plus 8 over 3n, and that has to stay. Okay. So I get the limit as n goes to infinity of 4 over n times. And what did I have? I had 21n plus 20. Just combining like terms there. 16n over 3 plus 8 over 3n. Great. Okay. Still have my limit. And I'll distribute the 4 over n through. 4 times 21 is 84, and the n's cancel. 4 times 20 is 80 over n. 4 times 16 is 64. The n's cancel, and I just have over 3. 4 times 8 is 32. And the bottom gets another n tacked onto it. Okay, we're almost there. It looks like now I'm in a proper place to apply my limit, but let's combine like terms first before I go doing that. And it turns out that when I add 84 to 64 over 3, I believe this is correct. 316 over 3 plus 80 over n plus 32 over 3n squared. I might have made a numerical mistake in here somewhere, but if so, it was just arithmetic. Then, feel free to email me and yell at me and tell me that I screwed up. So I get 316 over 3. This stays the same once I push n to infinity. This guy goes to 0, and so does this guy. So I'm left with 316 over 3. And that concludes the longest lecture of all time.